Hi, welcome to this animation on alkene stability. In this part, we will discuss how to rank alkenes in stability and the reasons for their order of stability. To find out how organic chemists use data to determine alkene stability, please view the animation Alkene Stability Part 2 that discusses heats of hydrogenation. Now let's start on this animation on alkene stability. We will first classify alkenes in terms of alkyl substitution. On the screen, we have line drawings on the top with R groups, and in the bottom section, ball and stick models where alkenes are substituted with methyl groups that correspond to the R groups. Ethylene is an unsubstituted alkene. Only hydrogen atoms are bonded to the carbon-carbon double bond. A monosubstituted alkene is one where one alkyl group is bonded to the carbon-carbon double bond. Let's turn that R group's color on the top line drawing to green. A disubstituted alkene is one that has two alkyl groups bonded to the carbon-carbon double bond. Cis and trans 2-butene are disubstituted alkenes. Let's turn those R groups' color on the top line drawing to green. 2-methyl-2-butene is an example of a trisubstituted alkene. A trisubstituted alkene is one that has three alkyl groups bonded to the carbon-carbon double bond. Let's turn those R groups' color on the top line drawing to green. And finally, 2,3-dimethyl-2-butene is an example of a tetrasubstituted alkene. A tetrasubstituted alkene has four alkyl groups bonded to it. Let's turn those R groups' color on the top line drawing to green. From heats of hydrogenation measurements, we know that the more alkyl groups around the carbon-carbon double bond, the more stable the alkene. So to show that general trend, let's rank the top line structures from the least stable alkene on the left to the most stable alkene on the right. How can we explain this trend? Let's remove all the ball and stick models from the screen except propene and cis-2-butene to explain why increasing the substitution around the carbon-carbon double bond stabilizes the alkene. There are two reasons that contribute to the fact that more substituted alkenes are more stable. First, cis-2-butene has two overlapping carbon sp2 to carbon sp3 sigma bonds, versus propene having only one. For every added carbon-carbon bond of this type, there is an increase in bond strength. The second reason for increased stability is that as we add alkyl groups to the carbon-carbon double bond, there is an increase in electron delocalization. To clearly see this in propene, let's first show as p orbitals that make up the pi bond. We will now show the orbitals of one of the methyl carbon's CH sigma bonds. This 2-electron bond is comprised of an overlapping sp3 hybrid orbital on carbon and an s orbital on hydrogen. This bond, with its electrons, in turn, overlaps with the adjacent p orbital of the alkene, resulting in an increase in delocalization of electrons. The sharing of electrons from an adjacent sigma bond into a p orbital is called hyperconjugation. A methyl group has three CH bonds that participate in the same way. 2-butene has two methyl groups, or a total of 6 sigma bonds, that can do this. This general trend continues through the series. So with each alkyl group added to the carbon-carbon double bond, we see an increase in stabilization. You may have noticed in the center of the top section that we have two disubstituted double bonds, specifically cis and trans disubstituted alkenes. Do they have the same stability? No. The cis compound is less stable than the trans compound. So let's place a less than sign between these two structures. The reason for this difference in stability is due to steric hindrance, making the cis alkene less stable. Let's compare ball and stick models of cis and trans 2-butene to visualize this difference. Now we will show the electron clouds for the cis methyl groups and the trans methyl groups. We can see that the proximity of the two methyl groups' electron clouds produces an unfavorable non-bonding interaction in the cis compound. This steric hindrance between methyl groups causes cis-2-butene to be less stable than trans-2-butene. In summary, the more substituted the carbon-carbon double bond, the more stable the alkene. This is due to increasing the stronger carbon sp2 to carbon sp3 bonds and more hyperconjugation. For disubstituted alkenes, cis-alkenes are less stable than transalkenes due to steric hindrance between the cis-alkyl groups. In order to find out how we determine alkene stability, view the Alkene Stability Part 2 animation. If you liked this video and would like to see more, please give it a thumbs up and subscribe.